electron spin resonance, or ESR, with electric fields replacing the magnetic fields. And one way to do this is through electric dipole spin resonance. So if we have a two-dimensional system with spin-orbit coupling and a constant real magnetic field as well as a parallel AC voltage are applied along this direction, then the AC voltage generates a time-dependent electric field, which through the spin-orbit interaction produces an oscillating effective magnetic field that's perpendicular to the constant real field. And so we have the conditions required for electron spin resonance in this system. More recently, it's also been demonstrated experimentally that we can have what's known as ballistic spin resonance. And in this case, there can be an oscillation of the momentum in time that comes from the ballistic motion of electrons through a channel with spin-orbit coupling. And this produces an oscillating effective magnetic field. And if a constant real field is applied perpendicular to this, then we again have spin resonance conditions. So now we can ask whether it's possible to have electron spin resonance entirely from spin-orbit coupling. And this is the idea that motivates the work that I'll be talking about here. And in particular, we can look at the case of a one-dimensional quantum wire. So if we look at the lateral confinement potential of a quantum wire, then by periodically varying the asymmetry of that lateral confinement as we move along the wire, we can produce spatially oscillating spin-orbit coupling. And because this is a periodic potential, we now have a superlattice with a band structure that's spin-dependent due to the spin-orbit interaction. So in order for these ideas to be physically relevant, we need to be able to implement them in a real system. And the system of interest in our group is a lanthanum aluminate strontium titanate heterostructure. And in this system, it's been shown that nanowires with widths as small as 2 nanometers can be created at the interface using a local voltage-induced metal insulator transition. It's also been shown in our group that highly asymmetric potential profiles can be built into these nanowires along their lengths. So in principle, we can use the same method to create lateral confinement asymmetry by applying these asymmetric pulses perpendicular to the wire. And if we vary the degree of that asymmetry periodically as we move along the wire, we can produce a spin-orbit superlattice. So in addition, spin-orbit coupling strengths of the order of 10 to the minus 12 electron volt meters have been measured at the interface of this system. So it's possible to have both perpendicular uniform and oscillating spin-orbit coupling within this system. So with the knowledge that we have a potential physical realization of these spin-orbit superlattice quantum wires, we can come back to their theoretical description. And the starting point for our description is a tight binding model that's been shown to be equivalent to the continuum Rashba Hamiltonian. And so if we have a Rashba-like term of this form, then we can write an equivalent tight binding model that describes a spin-dependent hopping with a hopping amplitude that's directly proportional to the Rashba spin-orbit coupling strength, alpha, and which also depends on the lattice constant A. And so if we calculate the energy spectrum for this Hamiltonian, then we find tight binding bands that are spin split along the momentum axis, which is what we would expect from the continuum version of the Hamiltonian. So we can now generalize this model for Rashba spin-orbit coupling to include not only a uniform term, but also a spatially oscillating one. And here, notice that the uniform effective field is along the x direction, while the spatially oscillating one is along the z direction. And so here you can see a spatially varying spin-orbit hopping amplitude for a period of m equals 4 lattice sites. And so we can classify the eigenstates for this system according to quasi-momenta associated with this periodicity. And here you can see the energy spectrum for a uniform spin-orbit strength of 1 relative to T naught, which is the hopping amplitude associated with the kinetic energy. And so if we now want to look for signatures of spin resonance, we can create a superposition of two states with equal and opposite quasi-momenta, and I'll call this superposition state a wave packet. So we can now look at the Fourier modes of the x component of spin polarization for this wave packet as we vary the strength of the uniform spin-orbit coupling. And here you can see that for the lowest non-zero Fourier mode, there's a peak at a value of 1. And if we look at the wave packet corresponding to this peak, and we vary the relative phase between the two eigenstates in the superposition, which is equivalent to looking at the time dependence of the wave packet, then here we see that the spin polarization oscillates, and this oscillation moves over the length of the wire as the phase is varied. But if we now look at a particular instant in time, then we see that while the y and z components of spin polarization oscillate rapidly over space, the x component oscillates more gradually, and it goes through one full cycle over the length of the wire. And we can understand this better if we look at the spin vector in the Bloch sphere picture. And here you can see that the spin spirals from up to down and back to up again, which is what we would expect for electron spin resonance. But now we're looking at the spin polarization as a function of the spatial coordinate. And so we see that these spin orbit superlattice quantum wires spatially map out electron spin resonance. So with this fully spin orbit electron spin resonance, we can potentially carry out single qubit gates. And to see how this would work, we can imagine applying spatial pulses using wire segments of fixed lengths. So for example, if we want to apply a pi/2 pulse, the wire segment might look like this, while for a pi pulse, we could have a wire segment like this. So in these systems, the quantum gate operations are essentially built into the band structure of the superlattice. And typically we think of electron spin resonance or a quantum gate as a time-dependent process. But in these systems, the gate is dependent only on how far the electron travels along the wire. And so it's potentially more robust to errors. We also have the fact that because this is a one-dimensional system, there is a built-in fault tolerance for backscattering, so that any change in spin polarization due to backscattering can be undone if the electron again scatters into its original direction. And what ultimately determines the spin polarization is the spatial coordinate. So as a specific example, we can consider the mapping of a spin echo pulse sequence from time to space. And so for time, the sequence consists of a pi/2 rotation, followed by a time interval of free evolution, and then a pi pulse, then another free evolution time interval equal to the first, and a last pi/2 pulse. And here we've added two time intervals of free evolution just to see the starting and ending points more clearly.
Before you start, go on.
Yeah.
So is the spin itself, does it have some energy splitting due to field, or what are you imagining?
Due to the spatially varying spin-orbit coupling.
No magnetic.
No, but I mean, you started with the spin pointing up, is that right?
Yeah, so, I mean...
What just, if they're degenerate, what prevents it from going to the down? Or what's the right basis?
Well, it's the
to
spin
use?
orbit eigenstates. So the spin is coupled to the quasi-momentum state.
Okay.
So that's basically the spatial degree of freedom determines the spin because of spin orbit coupling.
So are we talking about a spin that is, if it's, I guess what I'm asking is, if there's no magnetic field, what breaks time reversal symmetry?
Nothing.
Nothing in this
So
case.
what prevents it from scattering directly to the spin down state? Is it because, as you said, of the minus k not
Right.
being allowed?
Right.
Okay.
So, I mean, here we're taking a superposition of two states with equal and opposite quasi-momenta.
Okay. I
So-
see. So your actual state is basically plus k and minus k.
Mm-hmm.
Okay.
Right.
All right. I think you said that, but it
What
went
sort
very
of,
fast.
in the implementation you showed us
Mhm.
from the group, what sort of spin orbit strengths do you imagine you'll be able to access? I mean, normally spin orbit couplings or
They're
splittings
small.
are pretty small, right?
Yeah, well, I mean, it depends, I think, on the confinement also. So, for two-dimensional systems, for this lanthanum aluminate strontium titanate heterostructures of the order of 10 to the minus 12. But what's been shown more recently in
10
results...
to the minus 12 what?
Electron voltmeters, sorry. Sorry, I didn't realize I didn't say that. So, but in our group, actually, there's a lot of evidence that the spin orbit strength is much, much stronger than that in these nanowires that they're creating. So, and these are very, very narrow nanowires of the order of 10 nanometers. And so both the lateral spin orbit strength and the vertical one are actually enhanced in these nanowires, is what we think.
It's not just the gradient. I mean, it's stronger than what you would expect from the gradient. Is that what you mean?
Right.
I see. Okay. So again, coming back to my question, which is, I'm just trying to wrap my head around the exact state. So what you do is say, let's say you start with a state which is plus k spin up plus minus k spin down, right? That's your starting point.
Yeah.
And then when you do your, say, pi rotation, will that go to plus k spin up plus minus k spin down? Is that what you mean by a pi pulse in this particular?
So actually, I should probably back up. So look at this spectrum. So actually, these eigenstates are not states of a particular component of spin because of this perpendicular, uniform, and spatially oscillating spin-orbit coupling. So if you had only the uniform spin-orbit coupling, then they would be eigenstates of Z, for instance, or sorry, of X in this case, for instance, sigma X. But in this case, because we have the spatially oscillating spin-orbit coupling, these are actually not eigenstates of a definite spin. But if we take a superposition...
Right, that's what I said, which is they start out as a superposition, say, with a plus sign.
Okay, so you're saying the individual eigenstates?
Yes,
okay.
Right, and after your pi or pi over 2 pulse, does it go to a superposition with a minus sign? Is that what you mean? By the...
Yeah,
by your pi over 2 or pi rotation?
Yeah, so it's basically over space, you can see that the spin actually changes.
Yeah, I mean, it's not, you're so used to thinking about
so
dynamics. This is not actually
it's not dynamics. So it's a resonance in
variations.
space.
So space is time.
Right, but you still got to have some kind of...
the temporal dynamics is trivial, it's just a two-level system. So you get this beating and so forth. But the spin evolution is from the one end of the chain to the other. And that's
right.
determined
that
by
I
the arrangements
but,
of the...
okay. Well, okay, maybe I had to think about it something.
Right, so it's basically you can go from plus 0.5 to minus 0.5 over space.
Right, I understand that part, but what I was trying to get to was the question of what are the eigenstates in your system first.
Right. Yeah, so they're actually very complicated superpositions of 4 states in a subspace.
Exactly.
So, I mean, I have the exact expressions, but...
Yeah, so, but they're obviously very, yeah, okay.
Okay, so, this pulse sequence is typically used to cancel the effects of undesired spin evolution due to inhomogeneous magnetic fields, for example. But here we're using it to illustrate that we can carry out a sequence of single qubit gates in space. And so if we calculate we can build in this pulse sequence directly into the Hamiltonian through the spatially oscillating spin-orbit hopping amplitude. And if we calculate the spin polarization for a superposition of the 2 ground states of the system, then what we find is what we would expect for this pulse sequence in time. But and here you can again see the spin vector on the Bloch sphere. But this is in fact, again, the spin polarization as a function of the spatial coordinate. And so this mapping of quantum spin dynamics from time to space suggests a new way of performing quantum computation.
What was your plotting software that made that graph?
Mathematica?
The left graphs.
Oh, which one?
The left ones. That one.
This one?
Yeah,
Mathematica.
I've just never seen a plotting software where they're too lazy to subtract half the size of the dot. Unbelievable to me. I would fire the guy who wrote that software.
Not sure.
Half of the size of the dot, what are you talking about?
Look, the dots don't go on the lines. It's like, what are they doing?
I'm not sure.
Right. Look at the top
here?
line. All the dots are shifted.
Yeah.
It's like, good God, people.
Well, it's only a few pixels.
Look, I noticed it.
Okay.
Okay.
How are you going to...
Maybe there's some setting or something. But
I mean,
that's a flaw in Mathematica.
This analogy is interesting, but it isn't clear how you will actually use this to carry out a computation of anything.
Well, I mean, yeah, that's something that we're kind of working on, and actually we're thinking about generalizations of this to 2 qubits also. And so basically, you have these wire segments, but you need to be able to initialize it somehow and read out the final result somehow, and that's something we haven't considered yet. So
Okay,
is that more along the lines of what you were thinking?
Well, I couldn't see how you would actually use this effectively, and so the only thing I could catch was, well, it's sort of an analogy, an interesting analogy, but then already, in solid state physics, one has spin density waves and oddities like that, and so is there more to it than just a vague analogy? This was my question.
Well, I mean, so it's kind of inspired by the experiments that have been going on with the nanowires.
Yeah, but more generally, maybe he's asking about the, like, is there a more formal way that you can think about mapping the spatial dynamics onto the time-dependent Schrodinger equation?
Well, sure. So,
or how would you factor 15 with this?
Well, that's probably something for the future, maybe. But yeah. So I mean, right now this is. I mean, as far as we know, there's no such spatial mapping of quantum spin dynamics to space, and so this sort of suggests that, you know, basically formally, that we can map the time-dependent Schrodinger equation to a Schrodinger equation in space. And so that mapping between the two is something that, you know, we try to demonstrate using this example. So this is one particular example of that.
And I forget again, so what is changing from one point to the next? What's oscillating actually?
The spin orbit hopping amplitude.
And you control that how? With the super lattice of the nanowire? Is that what it is? So what is changing? The diameter of the nanowire?
The asymmetry of the lateral confinement. Of the
but how do you control that?
Well, so that's one of the things I was mentioning, is that we basically,
You had some potential, I remember.
Right.
Right.